At the heart of the largest galaxy we know, IC 1101, lies a black hole so massive it defies imagination. How can such a giant exist, and what does it mean for the universe around it? Tonight we'll uncover the secrets of this cosmic monster. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, do you think black holes are the most mysterious objects in the cosmos? Thank you for watching. Now let's begin. IC 1101 lies more than 1 billion light-years away in the constellation of Serpens, appearing as the dominant central galaxy of the cluster, known as Abell 2029. The distance is so great that light captured today by telescopes began its journey, when the Earth's continents were arranged differently and life on this planet was in an earlier stage of evolution. At such a scale of separation, the faint glow recorded on photographic plates or digital sensors carries the accumulated light of trillions of stars spread across a system larger than almost any other known galaxy. The perspective is not of a single isolated object, but of a central body embedded in a dense cluster where gravitational forces shape both individual members and the whole environment. Abell 2029 is one of the most massive galaxy clusters catalogued in the nearby universe. It is a gravitationally bound structure extending across millions of light-years, containing hundreds of galaxies, a pervasive halo of dark matter, and an enveloping medium of hot plasma. The existence of the cluster was first established by systematic surveys that mapped concentrations of galaxies on photographic sky plates. Subsequent measurements across optical and X-ray bands confirmed the richness of its membership and the enormous gravitational mass required to hold it together. IC 1101, located at its very centre, is identified as the brightest cluster galaxy. This designation reflects not only its luminosity, but also its position at the deepest part of the cluster's potential well, where surrounding galaxies gradually spiral inward over cosmic time. The immense scale of IC 1101 becomes apparent when astronomers attempt to measure its diameter. Photometric studies suggest that its faint outer envelope extends more than 1 million light-years from end to end, an order of magnitude larger than the Milky Way. While the Milky Way's stars form a relatively distinct disk structure, with a visible boundary, IC 1101 displays no such sharp edge. Its brightness gradually decreases outward, fading into the diffuse light of the cluster. Observationally, this requires long exposures and careful subtraction of background signals, because the distinction between galaxy and intracluster space becomes blurred. The gradual fall-off in brightness is one reason why defining the size of such a galaxy depends on convention often tied to the radius at which surface brightness drops below a chosen threshold. The extended halo surrounding IC 1101 is composed of stars that were once bound to smaller galaxies. Over time, these smaller members were drawn toward the center of the cluster by the process of dynamical friction, a slow interaction where orbital energy is transferred to the background medium, causing gradual decay of their orbits. When these galaxies merged with IC 1101, their stars were dispersed into the outer halo, leaving behind a diffuse glow that stretches far into space. Astronomers refer to this component as intracluster light, when the stars become more associated with the cluster than with any individual galaxy. In practice, the distribution is continuous, and separating what belongs to IC 1101 and what belongs to Abell 2029 is more a matter of definition than of physical boundary. The hot gas filling Abell 2029 provides another layer of context. Observations with X-ray telescopes show that the cluster is luminous at those wavelengths, indicating gas heated to tens of millions of degrees. This intracluster medium has a density far lower than air, yet extends over volumes measured in millions of light years, making it one of the dominant components of the cluster's baryonic matter. The gravitational field of the cluster holds this gas in place, and its pressure influences the ability of galaxies within the cluster to retain their own supplies of cooler gas. For a giant elliptical like IC 1101, the presence of such a hot medium suppresses the formation of new stars by stripping away or heating potential reservoirs of cool material. As a result, the starlight observed from IC 1101 comes primarily from older populations that have persisted for billions of years, rather than from ongoing bursts of star formation. The classification of IC 1101 as a CD galaxy reflects its unusual morphology. Such galaxies are characterized by very large diffuse envelopes extending far beyond the central bright region. In deep optical images, the core appears relatively compact, but as exposure time increases, layers of faint light are revealed, stretching outward until they blend with the cluster background. This morphology indicates a history of successive mergers and accretions, each adding stars to the outer regions. The designation CD itself arises from a scheme where D signifies a giant elliptical, and the additional C denotes the central placement within a cluster. These galaxies are recognized as unique environments where processes that dominate galaxy clusters manifest most clearly. Measurements of surface brightness profiles provide one way to quantify such an extended system. Astronomers plot brightness as a function of distance from the center, using data from wide field detectors. For ordinary elliptical galaxies, this profile follows a predictable curve known as the de Vaucouleurs law, a specific mathematical form describing how light decreases with radius. In CD galaxies like IC 1101, however, the profile deviates from this simple pattern at large, radii flattening out into a shallower slope. This indicates the presence of excess light beyond what a normal elliptical would display evidence for the extended halo produced by mergers. Such photometric signatures confirm the unique structure of IC 1101 and demonstrate that its formation history diverged from that of smaller systems. The stars inhabiting IC 1101 are predominantly old, with colours that lean toward the red end of the spectrum. Stellar populations can be studied through broadband photometry and spectroscopic analysis, which reveal the ages and chemical compositions of large ensembles of stars. The dominance of red giant stars implies that major episodes of star formation ceased long ago, leaving behind evolved populations that now make up the bulk of the galaxy's light. The lack of blue, short-lived massive stars indicates that no significant new starbursts have occurred in recent epochs. This is consistent with the idea that the hot intracluster medium prevents the cooling and condensation of gas needed to trigger ongoing star formation. Although the central regions of IC 1101 shine most brightly, the diffuse light in the outskirts contributes significantly to its total luminosity because it extends over such a vast area. When integrated across the full diameter, the cumulative output ranks among the most luminous galaxies known. This extreme brightness is not a sign of youth or vigor, but rather the collected glow of many past generations of stars. The absence of clear structural features such as spiral arms, dust lanes, or ongoing star-forming knots reinforces the classification of IC 1101 as a massive elliptical. Its smooth appearance reflects the random motions of stars orbiting in a gravitational potential dominated by the combined mass of stars' gas dark matter and the cluster environment. Seen through different observational windows, IC 1101 offers a layered picture. Optical data present the visible stars, infrared observations probe older and cooler stellar populations. X-ray maps reveal the pervasive hot gas, and radio observations sometimes detect faint emissions associated with past nuclear activity. Each wavelength adds context, and together they build the understanding that this galaxy is not isolated, but deeply tied to the cluster around it. Its mass-light distribution and stellar history are interwoven with the dynamics of Abell 2029, making IC 1101 a central piece in the study of how the largest galaxies grow and evolve. IC 1101 is remarkable for the faint halo that extends outward, until it dissolves into the background glow of Abell 2029. In long exposures, the galaxy does not appear as a sharply bounded object, but as a central brightness surrounded by an envelope of diffuse starlight. This outer region is the product of countless mergers, where smaller galaxies have been stripped apart and their stars dispersed into the periphery. The result is a luminous haze stretching for hundreds of thousands of light years, blending into the cluster's intracluster light so smoothly that defining a true edge becomes nearly impossible. Astronomers measure this envelope using surface brightness profiles, carefully plotting how intensity falls with radius. In ordinary elliptical galaxies, the decline follows a predictable form, but in the case of the brightest cluster member, the profile flattens at large distances. That flattening reveals an excess of stars compared with normal systems, evidence for the gradual build-up of a halo through accretion. Many of these stars are only loosely bound, their orbits influenced not just by the central galaxy, but also by the gravitational field of the entire cluster. In effect, the halo serves as a bridge between the galaxy itself and the larger structure that surrounds it. This diffuse component, often described as intracluster light, is extremely faint and requires special techniques to study. Observers must subtract background signals with great care and sometimes combine many exposures to reveal the glow. In Abell 2029, the boundary between IC 1101 and the cluster light is especially ambiguous, highlighting how deeply enmeshed the galaxy is in its environment. Estimates suggest that this faint light represents a significant fraction of the cluster's total luminosity, a testament to the number of galaxies disrupted and absorbed over time. The stellar populations inhabiting these outskirts are predominantly old and metal-poor. Spectroscopy shows that their chemical signatures differ from the high metallicity stars in the inner bulge, supporting the view that many of them originated in smaller galaxies with less enrichment. When those galaxies were drawn into the cluster core, their stars were stripped and spread across the halo. Alongside them are countless globular clusters, dense stellar systems that resist tidal disruption and now orbit at extreme distances from the center. Their distribution acts as a tracer of mass far into the halo, indicating that the visible light is embedded in a much larger dark matter envelope. Defining the true size of IC 1101 therefore becomes a matter of convention. Some astronomers use effective radii, the distance enclosing half the total light, while others define a cutoff at a chosen surface brightness. Either way, the values obtained are enormous, dwarfing those of typical ellipticals. The lack of a sharp edge reinforces the idea that the central system and the cluster background form a continuous structure with no simple boundary between them. The largest measured radii place IC 1101 among the most extended galaxies, known a natural consequence of its role as the gravitational anchor of Abell 2029. The kinematics of stars in these outer regions provide further insight. Velocity measurements show dispersions too large to be explained by visible stars alone, implying the presence of a massive dark matter halo. Gravitational lensing studies of the cluster confirm this, showing distortions of background light consistent with a vast reservoir of invisible matter. The diffuse halo of IC 1101 is therefore both a luminous record of past mergers and the observable counterpart of a much larger hidden structure that defines the cluster core. Even in these distant regions, some gas and dust persist. Most interstellar material has been stripped or heated by the intracluster medium, yet remnants survive as faint clouds detectable in sensitive spectroscopy. Dust grains imprint subtle absorption features on the light from background sources, revealing their presence even where they cannot be imaged directly. These components illustrate how complex the outskirts remain, shaped by processes of stripping, heating, and enrichment that operate over billions of years. Simulations of cluster evolution predict just such structures. Central galaxies grow extended halos as smaller members are absorbed, their stars stretched into streams that eventually smooth into diffuse envelopes. Observations of IC 1101 match these predictions, demonstrating that hierarchical assembly is not just a theoretical concept but a visible reality. The faint light arching across its outskirts is the fossil evidence of countless past encounters. Although the galaxy lies too far away for telescopes to resolve fine detail in its halo studies of nearer systems, reveal that such halos often contain tidal shells and streams. It is reasonable to expect that IC 1101 too once displayed such features, now largely mixed into a uniform glow. The presence of this diffuse light confirms that the galaxy's growth did not end in the distant past, but continued as the cluster evolved. The halo seen today is the cumulative product of those long processes, a veil of starlight surrounding the giant elliptical at the cluster's heart. IC 1101 does not sit in empty space, but is immersed in a vast atmosphere of hot plasma that fills the center of Abell 2029. This intracluster medium is made mostly of ionized hydrogen and helium heated to tens of millions of degrees. At such extreme temperatures, the gas shines brightly in X-rays, allowing space telescopes to map its distribution. These observations reveal that the emission peaks at the location of the central galaxy, showing that the density of hot plasma is highest in the core. The presence of such an atmosphere means that the stars and dark matter of the system are embedded in a much larger reservoir of energetic gas. The hot medium profoundly influences the fate of galaxies in the cluster. Smaller members that plunge toward the center lose their own interstellar material through ram pressure stripping, leaving behind only stars and dark matter. That stripped gas enriches the plasma with heavier elements forged in earlier generations of stars, so spectra of the X-ray glow show lines of iron, oxygen, and silicon. The central giant then finds itself surrounded not by cold gas that could form new stars, but by a searing medium that prevents condensation. This is why IC 1101 shines with the steady light of old stellar populations, rather than with bursts of young blue stars. The conditions of the intracluster medium act as a suppressive force, locking the galaxy into a quiescent state. Theoretical models once predicted that the dense core of clusters should experience cooling flows, where hot plasma loses energy and condenses into cooler gas, potentially feeding star formation. In practice, observations of Abell 2029 and similar systems show far less cooling than expected. Instead, some mechanism supplies heat to balance the energy lost through radiation. Feedback from the central supermassive black hole is considered the most likely source. Outbursts from the nucleus can drive jets or inflate cavities in the hot gas, redistributing energy over vast volumes. Even if such cavities are faint in Abell 2029 compared with more active clusters, the balance between cooling and heating still shapes the state of the medium, ensuring that gas remains hot and star formation suppressed. Mapping the plasma provides an indirect way to measure the mass distribution of the cluster. Because the gas settles into hydrostatic equilibrium, its density and temperature gradients reflect the gravitational field that confines it. By analysing these gradients, astronomers can estimate the total mass required, including dark matter. Results confirm that most of the mass of Able 2029 is invisible with stars and gas, accounting for only a small fraction. IC 1101 therefore sits at the bottom of an enormous dark matter, well surrounded by a hot atmosphere that both testifies to and depends upon that gravitational field. The interaction between the hot gas and the galaxy's halo is continuous. As stars age and die, they release enriched material into the medium while the medium itself strips gas from incoming galaxies. Over billions of years, this cycle produces the chemical signatures observed in the plasma today. The heavy elements in the intracluster medium demonstrate that many generations of stars in many galaxies have contributed to its enrichment. Thus, even though star formation in the central giant is largely quenched, its earlier history and the histories of its neighbours are preserved in the composition of the gas that now surrounds it. Comparisons with smaller groups and the local group of galaxies emphasize the unique character of cluster centers. In the Milky Way, cold molecular gas forms clouds that collapse into new stars, while in Able 2029 the environment is dominated by hot plasma that suppresses such activity. This contrast illustrates the role of a large-scale environment in determining galactic evolution. The extraordinary size and passivity of IC 1101 are not only consequences of its merger history, but also of the surrounding medium that prevents new growth through star formation. The intracluster medium also provides important tests for cosmology. The fraction of baryonic matter in clusters measured through the hot gas aligns with values predicted by models of the universe's composition. By studying clusters like Able 2029, astronomers verify that the distribution of matter on these scales is consistent with the cosmic inventory derived from the cosmic microwave background. The plasma around IC 1101 thus serves not only as a local influence, but also as a window into the structure of the universe as a whole. Technological advances have steadily improved the view of this environment. Observations with Chandra and XMM Newton have mapped the brightness and temperature of the gas, revealing smooth profiles that extend over millions of light years. Future missions with more sensitive spectrometers will refine measurements of turbulence, chemical composition, and cooling rates, providing even sharper insights into the processes that regulate cluster cores. For now, the evidence already shows that the central galaxy exists within a complex interplay of stars, dark matter, and plasma, each component influencing the others. IC 1101 is therefore not an isolated system, but the luminous core of a hot, massive atmosphere. Its stars shine quietly, its halo blends into intracluster light, and its gas environment glows in X-rays that tell the story of both suppression and enrichment. By studying this medium, astronomers trace the balance of cooling and heating, the record of chemical evolution, and the depth of the gravitational well that holds the cluster together. IC 1101 contains a stellar distribution that changes gradually from the dense bulge to the faint halo, offering a layered structure shaped by its long history of growth. At the very center, the stars are packed so closely that the surface brightness rises sharply, producing a compact luminous core. Moving outward, brightness declines but remains higher than expected for ordinary ellipticals stretching across scales of hundreds of thousands of light years. This arrangement is not random but reflects the gravitational equilibrium established after countless mergers and interactions. Every star, whether near the center or at the edge, traces an orbit defined by the combined pull of visible matter and an extensive dark halo. Measurements of stellar velocities reveal the dynamical state of the system. In the inner regions, absorption lines in the spectrum are broadened by extreme dispersions, often exceeding several hundred kilometers per second. Such high values show that stars are moving in random directions at very high speeds, balanced against the strong gravity of the central concentration. At greater radii, the dispersions decline but remain substantial, confirming that the gravitational field extends far into the halo. These data demonstrate that the luminous mass of stars is insufficient to explain the observed motions. A vast component of dark matter must dominate the potential shaping the trajectories of stars across the galaxy's full extent. The populations of stars vary with position. Spectroscopic studies show that those in the core are older and more metal-rich, having formed from enriched gas in the early universe. Their reddish colours mark them as evolved giants, with compositions that record rapid early star formation. In contrast, the stars farther out tend to be less enriched, consistent with origins in smaller galaxies that merged later. These chemical gradients serve as a fossil record showing that the galaxy formed from a combination of early rapid growth and later gradual accretion. Each merger deposited stars with different histories, and over time those populations mixed into the smooth distribution observed today. Globular clusters provide additional traces of structure. These dense star clusters orbit in large numbers throughout the system, many residing in the extended halo. Their spatial distribution reaches distances of hundreds of thousands of light-years, and their motions confirm that mass extends well beyond the visible starlight. Because globular clusters are resilient against tidal disruption, they preserve the memory of their origins. Many were brought in by galaxies that no longer exist as separate entities, their clusters now orbiting within the central giant. By studying their positions, velocities, and metallicities, astronomers reconstruct the sequence of mergers that built the enormous halo of IC 1101. When compared with smaller ellipticals, the structure of the central member of Able 2029 stands out as exceptional. Ordinary ellipticals follow light profiles that can be well described by the de Vaucouleurs law, with effective radii of a few kiloparsecs. In IC 1101, the effective radius is measured in the hundreds of kiloparsecs, and deviations from the simple law become pronounced at large distances. The flattening of the profile reveals the excess of stars added through hierarchical growth. Simulations of cluster evolution predict exactly such outcomes. As galaxies fall into dense environments, they are stripped of stars that contribute to the halos of central giants. The observations of IC 1101 thus validate theoretical models of hierarchical assembly. The dense bulge itself is nearly spherical and shows little sign of rotation. Velocity maps indicate that random stellar motions dominate rather than the ordered rotation characteristic of disk galaxies. This pressure-supported state is typical of massive ellipticals, and in the case of IC 1101 it reaches extreme values. The absence of disk-like features such as bars or spiral arms emphasizes the difference between giant ellipticals and star-forming galaxies. The smoothness of the bulge reflects violent relaxation, a process that erases asymmetries during major mergers and leaves behind a featureless equilibrium. The ages of stars provide a timeline of growth. In the central bulge, most stars are older than 10 billion years, showing that the dense core formed early in cosmic history. The outer halo contains populations that are slightly younger, although still ancient by human standards. This gradient implies that the inner regions assembled quickly, while the outskirts grew over a more extended period through successive mergers. By combining age metallicity and kinematic data, astronomers pieced together a chronology in which early rapid formation was followed by slow accretion, producing the layered structure seen today. Dynamical friction continues to influence the distribution. As smaller galaxies orbit within Abell 2029, they gradually lose energy and spiral inward. Each merger adds new stars clusters and dark matter to the central system. Over billions of years, this process has produced the immense halo and the smooth density profile that distinguishes IC 1101 from lesser ellipticals. Numerical models show that repeated mergers naturally build galaxies of this size, supporting the conclusion that IC 1101 is the product of hierarchical growth on the larger scales. Even in the farthest reaches of the halo stars remain tied to the gravitational field of the central system. Their orbits may be weakly bound, but they still trace the influence of the galaxy's mass combined with that of the cluster. The gradual transition between bound halo stars and free intra-cluster stars makes it difficult to define where the galaxy ends. What is clear, however, is that IC 1101 exerts control over a region so vast that it challenges the very definition of a galaxy. Its stellar distribution reflects not only its own past, but also the evolution of the cluster core itself. The structure of IC 1101 demonstrates how the largest galaxies grow through both early rapid collapse and later extended accretion. By studying its density profile, velocity dispersions, and chemical gradients, astronomers gain a window into the processes that shape galaxies at the extremes of mass and size. Each piece of evidence, from globular clusters to diffuse stars, records part of the story of assembly. Together they reveal a system that is both a single galaxy and a record of countless others that have merged into its light. IC 1101 is often described through its luminosity profile, the curve that shows how brightness falls away from the center as distance increases. Astronomers construct this profile by measuring surface brightness at successive radii and correcting for background light. In the innermost regions, the profile rises steeply, reflecting the dense concentration of stars in the bulge. Beyond the central peak, the curve declines, but unlike ordinary elliptical galaxies, it does not fall off rapidly. Instead, the slope flattens at large radii, creating an extended tail that stretches hundreds of thousands of light years. This excess light beyond the expected profile is one of the defining features of the galaxy and signals the contribution of stars gained through repeated mergers. Fitting mathematical functions to the profile provides a way to quantify these properties. Smaller ellipticals are well described by the de Vaucouleurs law, an exponential of the fourth root of radius. For IC 1101, this law fails to capture the outer halo, so astronomers turn to more flexible Circic functions or composite models that include both a compact bulge and an extended envelope. By adjusting these fits to the data, researchers estimate effective radii, total luminosities, and the proportion of light contained in different structural components. The numbers place this galaxy among the most luminous ever measured, with a total output more than 10 trillion times that of the Sun. To observe such faint light requires long exposures and careful calibration. Wide-field optical telescopes can trace the brightness profile across large angular scales, while space-based instruments provide clearer measurements in the core without atmospheric distortion. Combining these data produces a profile that spans from bright central arc seconds to faint outer regions visible only after hours of exposure. Each part of the curve reveals a different aspect of structure. The steep central rise reflects the density of the bulge, while the shallow decline records the history of accretion in the halo. Color information adds another layer of understanding. By comparing brightness in different filters, astronomers derive gradients that show how stellar populations vary with distance. The core of ICL 1101 appears redder, consistent with old metal-rich stars formed in the early stages of assembly. Farther out, the light becomes slightly bluer, indicating the presence of stars from less enriched progenitors. These smooth color changes match the idea of hierarchical growth, with the inner regions forming rapidly from enriched gas, and the outer halo built gradually from smaller, less chemically evolved galaxies. Spectroscopy complements photometry by providing kinematic and chemical measurements. Absorption features in the light reveal the velocities of stars and their metallicities. In the inner regions, velocity dispersions are extreme, matching the deep gravitational well of the bulge. At larger radii, the dispersions decrease but remain higher than in normal ellipticals, showing that stars in the halo are still dynamically linked to the galaxy's mass. Metallicity measurements confirm the color trends with higher values in the core and lower values outward, reinforcing the interpretation of layered assembly. The total luminosity inferred from the profile is staggering. Integrated across all radii, the galaxy outshines nearly every other known system. Yet this brilliance does not come from bursts of new star formation. Instead, it arises from the combined light of trillions of old stars shining steadily for billions of years. The dominance of red giant populations means the glow is uniform and long-lasting, lacking the transient brightness of blue stars. In this sense, luminosity reflects accumulated mass rather than ongoing activity, distinguishing ICO 1101 from star-forming galaxies, whose brightness is tied to short-lived populations. Scaling relations link luminosity with other properties. The Faber-Jackson relation connects total light with velocity dispersion, while the fundamental plane ties together luminosity effective radius and velocity dispersion. IC 1101 lies at the edge of these relations, pushing the limits of correlations derived from smaller galaxies. Its position provides a valuable test of whether these empirical laws apply at the highest masses. Deviations suggest that brightest cluster galaxies evolve differently, shaped more by mergers and environment than by the processes that govern ordinary ellipticals. The challenge of separating galaxy light from cluster light complicates luminosity measurements. Intracluster stars stripped from smaller members blend smoothly with the halo, making it difficult to decide where the galaxy ends. Some studies define operational boundaries, while others treat the entire envelope as part of the system. Regardless of definition, IC 1101 dominates the light of Abell 2029, contributing more than any other member combined. This dominance underlines its role as the gravitational anchor of the cluster. Comparisons with galaxies in younger clusters help trace evolution. At higher redshifts, central galaxies tend to have smaller halos and lower luminosities, suggesting that they continue to grow as clusters mature. Observations of IC 1101 therefore represent a late stage in this process, where repeated mergers and accretion have built one of the largest and brightest galaxies in the universe. Simulations of cluster evolution reproduce similar luminosity profiles, confirming that hierarchical growth naturally produces extended halos and flattened profiles at large radii. Technical refinements in imaging continue to improve these measurements. Advances in sky subtraction detector sensitivity and image processing reveal fainter features than ever before. Dedicated low-surface brightness surveys show that halos and streams are more common and more extended than previously thought. In the case of IC 1101, such techniques confirm the exceptional size of its profile, reinforcing its reputation as one of the largest stellar systems known. The luminosity curve stretching from the dense core to the faint outskirts encapsulates the entire history of its growth and provides a quantitative description of how extreme a galaxy can become. IC 1101 possesses a central bulge of extraordinary scale, a stellar concentration so dense that its luminosity dominates the inner profile of the galaxy. Within a relatively compact region, the mass locked in stars equals or surpasses the totals of entire smaller galaxies. This bulge glows with the light of old metal-rich populations whose presence signals rapid formation in the early universe. Observations of color and spectra show that the stars here are ancient, with most exceeding 10 billion years in age. Their high metallicity indicates that the gas from which they formed had already been enriched by multiple generations of earlier stars, pointing to a phase of intense star formation that occurred quickly and ended early. Once the original gas was consumed or stripped away further, star formation ceased, leaving the bulge to shine steadily with the accumulated light of evolved giants. The dynamics of the bulge reveal its unusual nature. Spectroscopic measurements show that the stars move with very high velocity dispersions, in some cases several hundred kilometers per second. Such values rank among the largest ever recorded, confirming that the gravitational potential well is extremely deep. Unlike disk galaxies, where rotation provides the main support against collapse, this bulge is pressure supported. Random stellar motions in all directions combine to maintain equilibrium, giving the system its nearly spherical, featureless appearance. Velocity maps across the bulge reveal little net rotation, reinforcing the picture of a galaxy built by violent relaxation and mergers rather than by ordered rotation. The light distribution of the bulge can be modelled with steep Circic profiles reflecting the high central concentration. High-resolution imaging reveals smooth isophotes, with only gradual variations lacking dust lanes or bars. The absence of internal structure indicates that repeated mergers have erased asymmetries, leaving a uniform relaxed system. In contrast to galaxies with active star-forming disks, the bulge of IC 1101 appears devoid of substructures, highlighting its identity as a classical elliptical core that has reached dynamical stability. Chemical abundances provide further insight into the formation timescale. Ratios of alpha elements to iron measured from spectral absorption lines are elevated. This pattern indicates rapid enrichment by core collapse supernovae, which produce alpha elements quickly before type-wire supernovae can contribute larger amounts of iron. The elevated ratios therefore point to a brief but intense epoch of star formation, truncated before slower processes could significantly alter chemical balances. Such evidence strengthens the case that the bulge assembled rapidly in the early universe and has since evolved passively. The central region also provides the environment for the galaxy's supermassive black hole. Although the black hole itself cannot be seen directly, its influence is reflected in the inner velocity dispersions and in scaling relations observed in other galaxies. The established correlation between bulge mass and black hole mass suggests that the central object in IC 1101 is among the most massive black holes known, potentially reaching tens of billions of solar masses. While direct dynamical measurements at such distances remain difficult, the evidence from velocity dispersions and bulge luminosity strongly supports the presence of an enormous black hole at the core. Interactions between this black hole and the surrounding plasma shape the energy balance in the bulge. Feedback from accretion episodes in the form of jets or outflows can inject energy into the intracluster medium, heating the gas and preventing it from cooling. Although IC 1101 appears relatively quiescent in terms of new star formation, the central black hole likely played a crucial role in establishing that quiescence by cutting off the supply of cold gas. The old stellar populations observed today are a consequence of that regulation, their light preserved long after the conditions for forming new stars disappeared. The size of the bulge pushes the concept beyond ordinary definitions. Effective radii extend to tens of kiloparsecs, and the stellar mass enclosed is measured in the trillions of solar masses. These values make the bulge of IC 1101 not just large but extreme, challenging the boundary between bulge and galaxy itself. In practice, the bulge is both the brightest part of the system and the anchor around which the halo extends. Its smooth appearance and enormous luminosity make it a template for the most massive galactic centers observed anywhere, Comparisons with other brightest cluster galaxies reinforce its exceptional status. While all such systems possess large bulges, few match the scale of IC 1101. Its central density, high metallicity and velocity dispersions place it at the top of the distribution, making it a benchmark for studies of galaxy formation. Observing its properties allows astronomers to test whether relations established for smaller galaxies extend to the most massive cases and where they break down. The bulge therefore serves not only as a structural component, but also as a laboratory for astrophysical theories. The evidence preserved in the bulge tells a story of rapid early assembly, subsequent dynamical relaxation, and long-term stability. Its stars record the chemical signatures of ancient starbursts. Its kinematics demonstrate the depth of its gravitational well, and its uniform light profile reflects the smoothing effects of mergers. The central black hole, hidden but influential, ties its growth to the stellar mass around it. Together, these properties define the bulge as the luminous heart of IC 1101, a region where the history of one of the universe's largest galaxies is written in light and motion. IC 1101 is home to one of the most massive black holes ever proposed, an object whose influence extends far beyond the immediate center. Direct observations of such an object are impossible at a distance of over 1 billion light-years, but astronomers infer its presence from the motions of stars and gas in the bulge, from scaling relations established in nearer galaxies, and from the galaxy's extraordinary luminosity and velocity dispersions. These lines of evidence converge to suggest that the black hole at the heart of IC 1101 ranks among the largest known, with estimates placing its mass in the tens of billions of solar masses. Such a figure far exceeds that of the black hole in the Milky Way, and even those in other massive ellipticals, marking it as an extreme product of galaxy and cluster evolution. The methods used to estimate this mass rely heavily on scaling relations. Observations across many galaxies show that black hole mass correlates with the velocity dispersion of stars in the bulge, a relation known as the m-sigma relation. For IC 1101, velocity dispersions measured at several hundred kilometers per second imply a central black hole far more massive than ordinary examples. Another relation links black hole mass with bulge luminosity, and given the brightness of IC 1101's core, the implied black hole is again extreme. While uncertainties remain, especially when extrapolating these relations to the very largest galaxies, the consistency of multiple methods strengthens the conclusion that a truly enormous object resides at the center. Indirect evidence comes also from the effect such a black hole would have on its surroundings. Accretion of gas onto a supermassive black hole releases vast amounts of energy, powering phenomena such as quasars and radio galaxies. IC 1101 itself does not shine as a bright quasar today, but past episodes of activity may have left signatures in the intracluster medium. X-ray observations of Abell 2029 reveal a dense central atmosphere that should cool rapidly, yet cooling is suppressed, likely due to heating from feedback associated with the central black hole. Even if no dramatic jets are visible at present, earlier outbursts could have injected energy into the plasma, maintaining the balance between cooling and heating. This indirect influence hints at the role the black hole plays as a regulator of its environment. The scale of the black hole's event horizon can be imagined in relative terms. The Milky Way's central black hole, Sagittarius A star, has an event horizon about 24 million kilometers across, comparable to the size of Mercury's orbit. A black hole in the tens of billions of solar masses would have an event horizon hundreds of times larger, spanning distances comparable to the orbits of the outer planets in our solar system, or even beyond. Although such scales are small compared with the size of the galaxy, they represent immense gravitational domains where nothing, not even light, can escape. The existence of such a horizon at the heart of IC 1101 exemplifies the extremes of cosmic physics. Accretion processes around such a black hole are shaped by the availability of gas. In the present epoch, the hot intracluster medium does not easily condense into cold material, so accretion is likely limited. This explains the relatively quiet state of the nucleus. However, in the past, when gas-rich galaxies merged into the cluster streams of material, may have fed the central black hole more vigorously. During those times, IC 1101 may have hosted an active galactic nucleus producing jets radiation and outflows capable of altering its environment. Evidence from other clusters shows that such activity can inflate cavities in the hot gas drive shocks and enrich the intracluster medium with heavy elements. It is reasonable to infer that the black hole in IC 1101 has undergone similar cycles of activity, even if today it remains dormant. The presence of such a massive black hole raises questions about formation pathways. Stellar mass black holes formed from the collapse of massive stars cannot grow to billions of solar masses in isolation. Instead, growth must come from repeated accretion and mergers of smaller black holes. In dense environments like cluster centers, such processes proceed efficiently. Each time galaxies merge, their central black holes sink toward the new center via dynamical friction, eventually coalescing. Over billions of years, this sequence of mergers produces the giant black holes seen in the most massive galaxies. IC 1101 at the hub of Abell 2029 represents the culmination of this process, with its central object embodying the cumulative history of countless mergers and accretion episodes. Observational limits make direct confirmation difficult. Measuring black hole masses through stellar kinematics requires resolving motions very close to the event horizon, something not feasible at the distance of Abell 2029. Instead, astronomers rely on indirect proxies scaling relations and modeling of the galaxy's overall dynamics. While this introduces uncertainties, the convergence of different lines of evidence leaves little doubt that the black hole is extraordinary. Future telescopes with larger apertures and more sensitive instruments may refine these estimates, but even current data place IC 1101 among the record holders. The relationship between the black hole and the host galaxy appears to be one of mutual regulation. The bulge provided the gas reservoir that allowed the black hole to grow, while feedback from the black hole helped shut down further star formation, locking the galaxy into a quiescent state. This coevolution is seen in other galaxies as well, but in IC 1101 it reaches the most extreme scale. The enormous bulge and the enormous black hole are linked products of the same history tied together by correlations that extend across the population of galaxies. IC 1101 thus provides one of the clearest examples of how black holes and galaxies grow together in cluster environments. The mass of the central object testifies to the accumulation of matter across cosmic time, while its influence on the intracluster medium demonstrates how even a compact source can regulate an entire cluster core. Though invisible directly, the black hole is a central component of the system's identity, shaping both the past and present state of the largest galaxy yet observed. IC 1101's central black hole draws material inward through the process of accretion, a mechanism that transforms gravitational energy into light and heat. When gas approaches the black hole, it does not fall straight in, but instead forms a rotating disk. In this accretion, disk matter spirals inward, compressed and heated to extreme temperatures by friction and magnetic forces. At high enough rates, the disk can shine more brightly than all the stars in the host galaxy combined, producing what astronomers call an active galactic nucleus. Although IC 1101 appears quiescent today, evidence from its structure and environment suggests that periods of intense activity occurred in its past when infalling galaxies supplied cold gas to feed the core. The physics of accretion disks is governed by the balance of gravity, rotation, and viscosity. Material at the outer edge of the disk orbits relatively slowly, while material closer in moves at relativistic speeds, approaching a significant fraction of the speed of light. Collisions and magnetic turbulence cause inner layers to heat to millions of degrees, emitting radiation across the electromagnetic spectrum. X-rays arise from the hottest parts near the event horizon, while ultraviolet and optical light emerge from slightly cooler regions farther out. By studying these emissions in active systems elsewhere, astronomers infer the processes that must also occur in extreme galaxies like IC 1101. As matter spirals inward, only a fraction crosses the event horizon. Much of the gas releases energy before being swallowed, and some is expelled back into space in the form of outflows or jets. The efficiency of this conversion is remarkable. Up to 10% of the rest mass energy of the accreted matter can be radiated away, far higher than the efficiency of nuclear fusion inside stars. This makes accretion onto black holes one of the most powerful energy sources known in the universe. For IC 1101, the enormous mass of the central black hole means that even brief episodes of accretion could have released enough energy to affect the surrounding intracluster medium on scales of hundreds of thousands of light years. Observations of other brightest cluster galaxies show signs of such feedback. Radio images reveal jets stretching far from their cores, and X-ray maps show cavities in the hot plasma where these jets displaced gas. Even though direct evidence for such cavities is less obvious in Abell 2029, the smooth temperature and density profiles of its gas suggest a balance maintained by some heating mechanism. The black hole of IC 1101 is the most likely source releasing bursts of energy whenever enough gas reached the accretion disk to ignite activity. This cyclical process, gas cooling feeding the black hole, feedback reheating the gas, keeps the cluster core stable, preventing runaway star formation, while allowing the galaxy to remain luminous with old stars. The scale of the event horizon itself highlights the extremes involved. A black hole of tens of billions of solar masses would possess a Schwarzschild radius of hundreds of astronomical units larger than the span of our solar system. Any matter that crosses this radius vanishes from the observable universe, but before reaching that point it can undergo violent transformations in the accretion disk. Relativistic effects near the event horizon distort the paths of photons bending light around the black hole and creating gravitational lensing that would alter the appearance of the disk to a distant observer. Although too remote for current instruments to resolve directly, models based on general relativity allow astronomers to predict how such a system would appear if it were closer. The relationship between accretion and feedback explains much of the evolution of the central giant. When gas is plentiful, the black hole grows and radiates, heating the environment and eventually reducing the inflow. When gas supply dwindles, the nucleus becomes quiescent, as IC 1101 appears today. Over cosmic timescales, these cycles repeat, each one leaving imprints on the structure of the galaxy and the cluster medium. The present state, with little active star formation and an enormous halo of old stars, reflects the long-term outcome of many such cycles. The black hole has both grown by accreting matter and shaped its host by regulating the availability of gas. Accretion also explains the scaling relations between black hole mass and host galaxy properties. The same processes that built the bulge of IC 1101 provided fuel for the black hole linking their growth. The balance between inflows and feedback established correlations observed across galaxies of all sizes. In IC 1101, the mass of the black hole sits at the extreme high end, consistent with the extreme luminosity and velocity dispersions of its bulge. These correlations suggest a universal mechanism operating across scales from small ellipticals to the largest cluster members, tying together the fate of stars and the fate of black holes. Although the nucleus of IC 1101 is not bright in the present epoch, astronomers search for subtle signs of activity. Weak radio emission, faint X-ray sources, or small disturbances in the intracluster medium can all indicate low-level accretion. Such activity may continue intermittently, fueled by occasional streams of gas stripped from infalling galaxies. Even if current rates are low, the black hole still exerts a dominant influence over its environment, its gravitational field shaping stellar motions and its feedback history, preserving the hot state of the cluster core. Future observations may refine our understanding of accretion in distant systems. More powerful X-ray telescopes will measure temperature fluctuations in the plasma with greater precision, while radio arrays will search for faint jets and lobes. Optical and infrared spectroscopy may detect subtle emission lines from ionized gas near the nucleus. Together, these tools will build a more complete picture of how accretion operates in the most massive galaxies. IC Sylvester 1, by virtue of its scale, will remain a crucial target for such studies, offering a chance to test theories of black hole physics at the very limits. The process of accretion is thus central to understanding both the growth of the black hole and the quiescent state of the galaxy. It links the invisible compact object to the visible stellar populations, the hot intracluster medium, and the overall balance of energy in the cluster. Though the galaxy appears calm today, its history includes phases of extraordinary activity, driven by matter spiraling into the heart of IC 1101. The traces of those phases remain in its structure, and in the state of the gas that surrounds it, silent witnesses to the immense power released by one of the largest black holes known. The scale of the black hole at the center of IC 1101 invites consideration of the event horizon itself, the surface beyond which nothing can escape. The event horizon radius grows in proportion to mass, and for an object of tens of billions of solar masses, this boundary extends hundreds of astronomical units from the core. Though such distances are small compared with the million light-year span of the galaxy, they represent a region so compact and dense that its escape velocity exceeds the speed of light. No signal particle or radiation can cross outward once it passes this limit. To an outside observer, the horizon marks the end of the observable universe for any material that ventures within. While the event horizon itself is invisible, the region around it produces signatures that can be studied indirectly. Gas spiraling inward heats up and radiates energy before being swallowed. The inner accretion flow can emit X-rays and even produce relativistic jets. Observations of active galactic nuclei elsewhere show how these processes unfold, and models predict similar behavior for IC 1101 during phases of higher activity. The balance between gravity pulling inward and forces within the accretion disk resisting collapse creates a dynamic environment where matter loses angular momentum and slowly drifts across the critical threshold. Once the boundary is crossed, the material vanishes from view, but the energy it released beforehand leaves imprints detectable even from 1 billion light-years away. The event horizon of such a massive black hole is not just a simple boundary, but also a gravitational lens. Light from stars or gas passing near the horizon can be bent around the black hole, producing distorted images and arcs. Simulations show how accretion disks would appear, with light from the far side bent over the top to create a ring-like outline. Although IC 1101 is far too distant for such detail to be resolved, the principles of general relativity ensure that these distortions occur. The Event Horizon Telescope has already imaged the horizons of black holes in nearer galaxies, And though similar work on IC 1101 is impossible at present, the same physical laws apply at its core. The scale of the black hole also influences time near the horizon. According to relativity, time passes more slowly in stronger gravitational fields. For material orbiting close to the horizon, processes would appear slowed when viewed from far away. Photons emitted from this region are also redshifted, losing energy as they climb out of the gravitational well. These effects combine to make the immediate environment around the horizon unique, a domain where ordinary intuition about space and time no longer holds. For IC 1101, such effects occur on scales vastly larger than those near smaller black holes, yet still tiny compared with the galaxy that hosts them. The mass of the horizon can be inferred indirectly through models that link stellar velocity dispersions, bulge luminosity, and black hole growth. For IC 1101, values in the tens of billions of solar masses have been proposed. This would make the event horizon one of the largest in the observable universe. Even if uncertainties remain, the magnitude of the estimate highlights how extreme conditions at the center must be. The gravitational sphere of influence of such an object extends thousands of light years, altering the motions of stars in the bulge and shaping the core's dynamics. Within that sphere, random stellar orbits reflect not only the collective gravity of the bulge, but also the hidden presence of the black hole. Relativistic jets are another consequence of matter interacting with horizons. In many systems, magnetic fields near the accretion disk channel, some inflowing material into narrow streams that blast outward at nearly the speed of light. These jets can carry energy far from the black hole, inflating lobes of radio emission and pushing aside hot plasma. Even if IC 1101 does not currently display strong jets, other galaxies of its class do, and it is likely that periods of jet activity occurred in its past. Such outbursts would have affected the state of the intracluster medium, helping to regulate cooling and maintain the balance of hot gas observed today. The study of event horizons in massive black holes provides a test of fundamental physics. General relativity predicts their properties with precision, and every observation so far supports those predictions. Yet horizons remain extreme environments where quantum effects may eventually need to be considered. Although IC 1101 lies too far away for direct probes, its central black hole stands as one of the best natural laboratories for such theories, demonstrating the upper limits of black hole growth and the immense scales at which horizons can exist. The influence of the horizon extends indirectly to the broader galaxy. By controlling how matter accretes, it dictates the release of energy into the surrounding medium. By growing in tandem with the bulge, it reinforces the correlations between black hole mass and galaxy mass. And by powering feedback processes, it determines whether gas can cool to form new stars or remains suspended in a hot state. The event horizon itself is a silent boundary, but the processes around it link the fate of the black hole with the fate of IC 1101 as a whole. Future instruments may provide sharper tests of these ideas. X-ray observatories will probe the innermost accretion flows, radio arrays will detect faint jets, and advances in interferometry may one day allow horizon-scale imaging at greater distances. For now, astronomers rely on indirect evidence and scaling relations to characterize the core of IC 1101. What emerges is a picture of one of the largest black holes in existence, with an event horizon spanning hundreds of astronomical units and influencing a galaxy that itself is one of the most massive known. The event horizon is therefore both a boundary and a symbol of extremes. It represents the point of no return, the invisible surface that defines the black hole. In IC 1101, this horizon is scaled to the size of the most massive galaxy, a gravitational landmark hidden at the cluster's heart. Although no telescope can yet resolve it, the evidence for its existence is overwhelming, written in the motions of stars, the luminosity of the bulge, and the balance of the surrounding medium. IC 1101 has not always appeared as calm as it does today. At different times in its history, the galaxy's nucleus has likely passed through phases of intense activity, when gas spiraling into the black hole released energy on scales capable of outshining all the stars combined. Such phases are known as active galactic nuclei, and when the activity is especially strong, they produce quasars. In the present epoch, IC 1101 is quiet, its core radiating steadily, but without the brilliance of an active quasar yet. Indirect evidence points to earlier episodes when it must have been much more luminous. The surrounding intracluster medium, enriched with heavy elements and maintained at high temperatures, carries the imprint of feedback processes that almost certainly involved energy released by the central engine. Active galactic nuclei arise when significant amounts of cold gas reach the accretion disk. The hot plasma that now dominates Able 2029 resists cooling, but in the past, infalling galaxies may have delivered reservoirs of cold material to the core. When that happened, the black hole would have drawn matter inward at high rates, producing radiation across the electromagnetic spectrum. Optical observations of other galaxies show bright emission lines from gas ionized by such activity, while radio observations revealed jets launched along magnetic field lines near the event horizon. X-ray data capture the hottest regions of the accretion disk. Although IC 1101 today lacks these strong signatures, scaling relations and the balance of energy in its environment suggest that it underwent similar activity in earlier epochs. The distinction between active and quiescent states depends not on the black hole itself, but on the availability of fuel. When mergers supply gas, the nucleus lights up. When fuel is exhausted, it fades. Over cosmic timescales, galaxies alternate between these states. In IC 1101, the enormous halo and old stellar populations show that star formation has been quenched for a long time, but that quenching may itself be a consequence of past activity. Energy released from the active nucleus could have heated and expelled gas, shutting off further star formation. This feedback cycle is observed in many clusters where cavities in the hot gas coincide with jets from central galaxies. Even if cavities in Able 2029 are less dramatic, the overall smoothness of the X-ray emission points to a regulated state maintained over billions of years. Jets are among the most visible products of nuclear activity. Launched at nearly the speed of a light, they can extend hundreds of thousands of light years into space-inflating lobes of radio emission and stirring the hot plasma of the cluster. The physics of jet launching involves magnetic fields threading the accretion disk and extracting rotational energy from the black hole itself. In IC 1101, direct evidence for such large jets is limited by distance, but the similarity of its environment to that of other active systems makes their past existence plausible. The enrichment of the intracluster medium with heavy elements also implies that material processed in galaxies has been redistributed, a task often accomplished by jets and outflows. When active, the nucleus could also have contributed to the reionization of surrounding gas. Ultraviolet photons from the accretion disk would have ionized hydrogen in the core, while shocks driven by outflows would have raised the temperature of the intracluster medium. These processes help explain why the gas remains hot and resistant to cooling flows. Without such heating, the plasma would condense into cold clouds that could form stars. Instead, star formation has been suppressed, leaving IC 1101 luminous with old populations but devoid of significant new growth. The absence of blue light in its spectrum is thus a legacy of feedback from earlier epochs of nuclear activity. The variability of active galactic nuclei also provides clues about their nature. In some systems, the brightness of the core changes over timescales of days or even hours, reflecting the small scales of the accretion disk compared with the galaxy. For ICLN-01, such variations are undetectable at its distance, but the principle holds: the larger the black hole, the longer the characteristic timescales of variability. For a black hole of tens of billions of solar masses, processes near the event horizon unfold slowly compared with smaller systems. This scaling means that any fluctuations in brightness during active phases would have stretched over months or years, yet still carried immense energy output. Understanding the active states of IC1101 also contributes to knowledge of black hole demographics. Quasars observed at high redshift show that billion solar mass black holes already existed when the universe was less than 2 billion years old. The central object in IC1101 likely grew through similar processes, but continued to accumulate mass as the cluster evolved. Each merger brought in not only stars but also smaller black holes that coalesced into the growing central one. The history of its activity is therefore intertwined with the history of the cluster itself, reflecting the broader narrative of hierarchical growth. Astronomers study nearby active galaxies to infer what IC1101 must have experienced. In systems like Perseus A and Virgo A, radiojets and X-ray cavities demonstrate feedback in action. Observing these analogues helps fill the gap for Able 2029, where distance makes such details difficult to resolve. By comparing environments and scaling up the processes, researchers conclude that IC1101 has undergone similar cycles, each one altering its surroundings and reinforcing its role as the dominant member of the cluster. The transition from active to quiescent state does not erase evidence of past activity. The chemical composition of the intracluster medium, the suppression of star formation, and the enormous mass of the black hole all testify to a history of accretion and feedback. Even if the nucleus today is quiet, the galaxy as a whole carries the marks of its energetic past. The smooth glow of old stars may seem placid, but behind that calm lies a record of violent episodes, when the core burned brighter than trillions of suns. The active galactic nucleus of IC1101 may no longer shine, yet its legacy endures. The cluster's hot gas remains suspended in equilibrium, the stellar populations are old and stable, and the central black hole rests at a mass achieved only through long cycles of growth. The story of activity and quiescence explains both the current appearance of the galaxy and the processes that shaped it, revealing how feedback from a single compact object can determine the fate of the largest stellar system in the known universe. IC1101's periods of nuclear activity have not only produced energy, but also shaped the broader environment through feedback mechanisms that extend across the cluster core. Feedback describes the process by which outflows from the black hole interact with surrounding matter, influencing the state of the gas and the ability of galaxies to form stars. In the case of the brightest cluster galaxies, such feedback is essential to explaining why they contain old red populations rather than ongoing bursts of star formation. Without a heating mechanism, the dense intracluster medium would cool and condense, producing large flows of gas toward the center. The absence of such cooling flows in Able 2029 points to the role of IC1101's central engine as a stabilizing force. One form of feedback involves relativistic jets launched from the vicinity of the black hole. These narrow streams of plasma can propagate far into the surrounding gas-inflating cavities and lobes that appear in X-ray and radio maps. As the jets push aside the hot plasma, they transfer energy into the medium, offsetting cooling. Observations of other clusters reveal pairs of cavities symmetrically placed around the central galaxy, sometimes connected to filaments of cooler gas. Even though Able 2029 shows fewer dramatic cavities, than some well-studied systems like Perseus, its smooth gas profiles still indicate that heating processes are at work. IC 1101's central black hole likely produced outbursts in the past that injected enough energy to maintain equilibrium across the core. Another feedback channel is the release of winds and radiation from the accretion disk. High-energy photons can ionize and heat the intracluster gas, while slower winds distribute metals and momentum into the surrounding medium. These processes are less dramatic than jets, but contribute steadily to the energy balance. The result is a system where cooling is moderated and gas remains hot, rather than collapsing into new stars. This balance explains the old red stellar populations in IC 1101 and the absence of recent star formation in its bulge. The smoothness of its stellar light profile, free of blue knots or spiral arms, is a visual confirmation of long-term suppression. Feedback has consequences beyond star formation. By redistributing energy, it changes the density and temperature structure of the intracluster medium, which in turn affects how galaxies orbit and evolve within the cluster. Heated gas expands, reducing central density and altering pressure gradients. This influences the dynamics of smaller galaxies that pass near the core, enhancing stripping and accelerating their merger into the central system. Thus, feedback indirectly contributes to the growth of IC 1101 itself, both by quenching its own star formation and by encouraging the assimilation of neighbors. Chemical enrichment patterns also point to feedback. The intracluster medium contains heavy elements such as iron and silicon, products of stellar nuclear synthesis. These elements must have been expelled from galaxies and distributed widely, a task facilitated by outflows from active nuclei. Past activity in IC 1101 likely played a role in dispersing enriched material across the cluster core, ensuring that the hot gas observed today contains signatures of many generations of stars. This enrichment connects the life cycles of individual stars to the evolution of the entire cluster, with the black hole acting as the agent that spreads their products across millions of light years. The feedback cycle can be described as self-regulating. Gas in the cluster core cools and begins to flow inward, fueling the black hole. As the black hole accretes, it releases energy that reheats the gas, halting the inflow. When activity subsides, cooling resumes, starting the cycle again. Over cosmic timescales, this process produces a dynamic balance, neither allowing catastrophic cooling nor extinguishing activity completely. For IC 1101, the outcome is a galaxy that remains luminous, with old stars but largely inactive in terms of new growth, its black hole occasionally reigniting to maintain equilibrium in the surrounding medium. Simulations of galaxy clusters confirm the importance of such cycles. Models without feedback predict central galaxies far brighter and bluer than those observed with excessive star formation. Only by including energy input from black holes do simulations reproduce the quiescent massive ellipticals seen in reality. IC 1101 provides an observational counterpart to these models, embodying the effects of feedback on the grander scale. Its existence validates the idea that supermassive black holes, though tiny compared with galaxies, control the thermal history of cluster cores. The study of feedback in IC 1101 also informs our understanding of cosmic structure formation. Clusters are among the largest bound objects in the universe, and their baryonic content is dominated by hot gas. Understanding how that gas remains hot despite radiating energy and X-rays is a central question in astrophysics. The role of feedback provides the answer. Energy released from accreting black holes offsets radiative losses, stabilizing the medium. IC 1101, by virtue of its scale and central position, is the clearest example of how this mechanism operates. Its black hole, though invisible, dictates the thermodynamic state of matter across millions of light years. Observational campaigns continue to probe feedback in cluster centers. Deep X-ray images search for subtle cavities or ripples in the plasma. Radio surveys look for faint relics of jets long faded. Spectroscopic studies map the distribution of metals to trace outflows. Each method contributes to the picture of how feedback operates. In Abell 2029, the evidence may be more subtle than in some clusters, but the principles remain the same. The absence of large cooling flows and the stability of the hot gas are sufficient indicators of the central engine's past influence. Future telescopes will sharpen this picture. The next generation of X-ray observatories will measure turbulence and sound waves in the plasma, revealing how energy is transported. Radio arrays with greater sensitivity will detect fainter lobes and relic structures. Optical and infrared instruments will search for traces of ionized gas close to the nucleus. Together, these efforts will refine the understanding of feedback in IC 1101, showing in greater detail how its central black hole shapes not only the galaxy, but also the entire cluster environment. IC 1101 therefore exemplifies the principle that the largest galaxies are regulated not by their stars alone, but by the compact objects at their centers. Feedback from the black hole governs star formation chemical enrichment and the thermal state of the intracluster medium. Through cycles of activity and quiescence, it has maintained the balance observed today, a giant elliptical glowing with old stars surrounded by hot plasma and resting in equilibrium within one of the most massive clusters known. IC 1101 has not produced new stars for a very long time, and this absence of star formation is one of the defining characteristics of its current state. Astronomers study the history of star formation in such systems by examining the colors and spectra of their stellar populations. The reddish hues of the galaxy's light indicate that its stars are old, dominated by low-mass, long-lived stars that emit more strongly at longer wavelengths. Spectroscopic studies confirm that there are few, if any, signs of young, massive blue stars which would indicate ongoing formation. Instead, the evidence points to a quenching of star formation billions of years ago, leaving behind a fossil record of earlier, more active times. The mechanisms that shut down star formation in IC 1101 are closely linked to its environment. In the dense centre of Abell 2029, cold gas, the essential fuel for new stars, is scarce. Any galaxy that plunges into the cluster is stripped of gas by ram pressure as it moves through the hot intracluster medium. For the central giant, the problem is even more acute. The surrounding plasma is heated to tens of millions of degrees, making it nearly impossible for gas to cool and condense into star-forming clouds. Even if cold gas occasionally reaches the center, through a merger feedback from the supermassive black hole, reheats it, halting the process before new stars can form in significant numbers. Astronomers reconstruct the star formation history by measuring the relative abundances of elements in the stellar populations. Ratios of alpha elements to iron indicate how rapidly star formation occurred in the past. In IC 1101, these ratios suggest that most stars formed in a short, intense burst, early in cosmic history, followed by a sharp decline. The enrichment of the central stars shows that many supernovae exploded in that early phase, producing heavy elements and distributing them through the gas from which subsequent stars formed. After this period, star formation fell dramatically, leaving behind a population that has simply aged ever since. The quenching of star formation is also reflected in the galaxy's morphology. Spiral galaxies with active star formation show dust lanes, bright star-forming knots, and irregular structures associated with molecular clouds. By contrast, IC 1101 exhibits a smooth elliptical profile free of such features. This smoothness is the visual result of both dynamical mixing during mergers and the absence of new stellar generations to create patchy light distributions. The regularity of its appearance reinforces the conclusion that the galaxy has been quiescent for billions of years. Quenching in brightest cluster galaxies can be compared with similar processes in smaller systems. In isolated galaxies, star formation may decline gradually as gas is consumed. In dense clusters, however, external processes accelerate the transition. The hot intracluster medium strips gas while feedback from central black holes adds further suppression. The result is a more rapid and complete end to star formation, producing massive ellipticals like IC 1101 that shine with old stars but no longer build new ones. These galaxies are described as red and dead, a phrase that captures both their color and their lack of activity, though in scientific terms they remain dynamically complex and luminous. The timeline of quenching can be estimated by comparing the ages of stars across different regions. In IC 1101, the stars in the core are the oldest, suggesting that the bulge formed first in a rapid burst. Stars in the outer halo appear slightly younger on average, consistent with later mergers that added pre-existing populations from smaller galaxies. However, even those stars are billions of years old, showing that the entire system has been quiescent for much of cosmic history. This pattern matches hierarchical growth models where central galaxies assemble early and then grow in mass through mergers rather than through fresh star formation. The chemical signatures in the intracluster medium also record the end of star formation. Heavy elements observed in the hot plasma must have been produced in stars and expelled during supernova explosions. Their presence indicates that galaxies in the cluster once formed stars at high rates. The absence of new contributions in recent times suggests that the era of active enrichment ended long ago. In IC 1101, the enrichment of the surrounding medium combined with the old stellar populations demonstrates that the system's star-forming days are firmly in the past. Comparisons with galaxies at higher redshifts provide further context. Observations of clusters when the universe was only a few billion years old show central galaxies that are still forming stars. Over time, these galaxies transition to quiescence, paralleling the path IC 1101 must have followed. By studying these younger systems, astronomers trace the sequence of events that leads to the state observed today. IC 1101 represents the endpoint of that process, a giant elliptical whose mass continues to grow by merging with other galaxies, but whose star formation has effectively ceased. The quenching of star formation also explains the galaxy's uniform color. Without new blue stars to add variation, the light is dominated by old populations, creating a consistent red appearance across the entire structure. Color gradients still exist, with the core slightly redder and the halo slightly bluer, but overall the effect is one of homogeneity. This uniformity is one of the observational signatures of quiescent galaxies and allows astronomers to distinguish them from younger, more active systems even at great distances. Although star formation in IC 1101 is minimal, it is not necessarily zero. Sensitive observations occasionally detect weak emission lines in massive ellipticals, suggesting small amounts of residual activity. Such low levels may be fueled by minor accretion of gas or by recycled material from dying stars. However, these rates are insignificant compared with those in star-forming galaxies, and do not alter the overall character of IC 1101 as quiescent. Its future will remain one of passive evolution, with stars aging and fading, but no substantial new generations to replace them. The study of quenching in IC 1101 provides a crucial data point for theories of galaxy evolution. It shows how environment, feedback, and merger history combine to halt star formation in the largest systems. By examining its stars, its colours, and its spectra, astronomers reconstruct the timeline of activity and inactivity, building a narrative that extends from early bursts of star formation to the quiet glow of old populations today. IC 1101 stands as an example of how galaxies reach maturity, trading youthful vigour for enduring stability in the heart of a massive cluster. IC 1101 provides one of the clearest opportunities to study gravitational dynamics on a galactic and cluster-wide scale. The motions of its stars, globular clusters, and satellite galaxies are determined not only by the luminous matter, but also by a massive halo of dark matter that envelops the system. Dark matter cannot be observed directly, but its presence is inferred from the way visible matter behaves. In the case of IC 1101, velocity dispersions measured across vast distances remain far too high to be explained by stars alone. The extended halo of diffuse light is embedded in an even larger invisible framework that dominates the mass budget. By modelling stellar kinematics, astronomers determine that dark matter outweighs the visible matter by a significant margin, confirming that the galaxy sits in one of the deepest gravitational wells known. The concept of velocity dispersion is central to these conclusions. Stars orbiting within the galaxy do not all move in the same direction. Instead, they follow random paths with speeds that can be measured spectroscopically through the broadening of absorption lines. In IC 1101, these dispersions reach several hundred kilometers per second, values that imply an enormous gravitational pull. If only the stars and gas seen in optical light were present, dispersions would be far smaller. The discrepancy reveals the existence of dark matter, a component that exerts gravity but does not emit light. When models, including dark matter, are applied, the observed dispersions match predictions, strengthening the case for its dominant role. Gravitational lensing provides an independent measure of mass. The light of background galaxies passing near Arbel 2029 is bent by the cluster's gravitational field, producing distortions that can be measured statistically. Analyses of these lensing signals show that the mass of the cluster is immense and that most of it is invisible. IC 1101, sitting at the core, is embedded in this halo, with its stellar distribution tracing only the densest inner region of a far larger structure. In combination with kinematic measurements, lensing confirms that dark matter is not confined to the galaxy itself, but extends across the cluster, shaping the dynamics of every member. The gravitational field of IC 1101 also influences the orbits of other galaxies in Arbel 2029. As smaller galaxies move through the cluster, they lose energy through dynamical friction, a process where gravitational interactions with the background of stars and dark matter slow them down. Over time, they spiral toward the center, merging with the giant elliptical and adding their stars to its halo. This mechanism explains the gradual growth of IC 1101 and the presence of diffuse intracluster light. It also ensures that the central galaxy will continue to accrete mass even in the absence of star formation, because its position at the bottom of the gravitational potential well makes it the inevitable destination for infalling systems. Simulations of cluster formation reproduce these processes in detail. Starting from initial fluctuations in the early universe, dark matter collapses into halos that attract gas and form galaxies. Over billions of years, these halos merge into larger structures, culminating in clusters. The central galaxy forms as the repeated mergers of massive halos produce a dominant member at the core. IC 1101 is the real-world outcome of such a simulation, a galaxy whose size and mass reflect the cumulative history of many mergers. The agreement between simulations and observations supports the current cosmological model, in which dark matter plays the primary role in structuring the universe. The scale of the dark matter halo surrounding IC 1101 can be appreciated by comparing it with its visible extent. While the luminous halo extends several 100,000 light-years, the dark matter halo is thought to reach several million light-years, overlapping with the cluster's total size. This invisible envelope ensures that the gravitational potential of the cluster is deep enough to confine hot plasma, explaining the presence of the dense X-ray emitting intracluster medium. Without such a dark matter, the plasma would disperse into intergalactic space. Thus dark matter not only shapes stellar motions, but also governs the thermodynamics of the gas. Stellar streams and globular clusters serve as traces of this invisible structure. Globular clusters orbit at great distances from the center, their motions reflecting the mass enclosed within their paths. By measuring their velocities, astronomers can extend mass estimates to regions where starlight is faint. In IC 1101, the distribution of clusters and their speeds confirm that dark matter dominates the outer halo. Stellar streams, remnants of disrupted galaxies, also align with predictions of dark matter, dominated models weaving faint threads across the diffuse light. Each stream tells the story of a past merger and provides another clue to the shape of the gravitational potential. The presence of dark matter also affects gravitational interactions on larger scales. As galaxies orbit within the cluster, the tidal forces of the massive central halo strip away their outer stars, feeding the intracluster light. This stripping process depends on the depth of the potential well, which in IC 1101 is greater than in almost any other known system. The result is a continuous blending of galaxy and cluster, where boundaries are blurred, and the central elliptical appears as both an individual galaxy and a manifestation of the cluster's mass distribution. Dark matter in IC 1101 connects local observations with global cosmology. The ratio of dark matter to visible matter matches predictions from measurements of the cosmic microwave background, showing that the same processes shaping this single galaxy also operate across the universe. Clusters like Abell 2029 serve as laboratories where the interplay between dark matter stars and gas can be tested. IC 1101, with its exceptional size and brightness, anchors these studies, providing a luminous point of reference for the invisible mass around it. The gravitational dynamics of IC 1101 demonstrate the complexity of the largest structures in the universe. Its stars move under the influence of both visible and invisible matter. Its halo grows through the gradual assimilation of smaller systems, driven by the drag of dynamical friction. Its hot gas is confined by the weight of a massive dark matter envelope, and its position at the center of Abell 2029 makes it both a galaxy in its own right and a component of a much larger structure. By studying these dynamics, astronomers uncover not only the story of one galaxy, but also the principles that govern the evolution of cosmic structures on the grandest scales. IC 1101 is so massive and luminous that it serves as a crucial test case for the observational techniques astronomers use to study the largest galaxies. No single instrument or wavelength reveals its full character. Instead, multiple methods across the electromagnetic spectrum are combined to form a coherent picture. Optical observations capture the starlight, allowing surface brightness profiles and color gradients to be measured. Infrared observations penetrate dust and highlight the contributions of older cooler stars. X-ray instruments reveal the hot plasma of the intracluster medium, while radio telescopes detect faint emission from past or ongoing nuclear activity. Each window provides a different perspective, and together they confirm the extraordinary scale and complexity of the galaxy at the heart of Abell 2029. Optical imaging remains the most direct way to trace the distribution of stars. Wide-field cameras on large telescopes can detect the faint halo of IC 1101 extending to radii, where brightness falls to only a fraction of the sky background. Long exposures and careful subtraction of background light are essential, since the halo is barely brighter than the cosmic night sky. These optical measurements reveal the smooth, featureless profile expected of a giant elliptical, but with an extent unmatched by typical galaxies. Spectroscopic follow-up provides velocities of stars and clusters translating light into dynamical information that constrains the gravitational potential. Infrared observations add detail by reducing the effects of dust and by highlighting the contributions of cooler stars that dominate the old stellar populations. Space telescopes such as Spitzer and the James Webb Space Telescope provide stable platforms for measuring faint infrared light without atmospheric interference. In IC 1101, infrared imaging confirms the dominance of evolved red stars and the absence of significant young populations. It also helps refine stellar mass estimates by providing light that more directly traces the bulk of the population rather than the luminous outliers. X-ray telescopes provide a very different view, one not of stars but of the hot plasma that fills the cluster core. Observations from Chandra and XMM Newton show the bright glow of gas heated to tens of millions of degrees. The smoothness of the emission and its central concentration reflect both the depth of the gravitational well and the regulating role of the central black hole. Temperature maps reveal gradients that trace cooling and heating processes, while spectroscopy identifies heavy elements dispersed throughout the medium. These X-ray data confirm that the intracluster medium outweighs the stars and is essential to the overall mass balance of Abell 2029. Radio observations complement these pictures by searching for emission from relativistic particles accelerated near the galaxy's core. Even when a nucleus is not bright in optical or X-ray bands, radio surveys can reveal jets, lobes, or relic structures that mark past episodes of activity. In other clusters, radio maps show vast cavities where jets from central galaxies pushed aside the hot plasma. For IC 1101, the radio emission is relatively faint, consistent with a quiescent state, yet its presence supports the idea that the black hole has undergone cycles of activity that influence the surrounding environment. Spectroscopy across all wavelengths is essential for disentangling stellar populations and gas dynamics. In the optical and near-infrared absorption lines reveal the ages, metallicities, and motions of stars. In the X-ray emission lines provide the chemical composition and temperature of the hot plasma. In the radio, spectral shapes indicate the ages of relativistic particles in jets and lobes. Each technique builds a piece of the puzzle, and together they create a consistent story of an ancient massive galaxy embedded in a rich cluster environment. The challenge of observing IC 1101 lies not only in distance but also in brightness contrast. The central regions are extremely bright while the outskirts are faint. Instruments must cover a wide dynamic range to capture both without saturation or loss of sensitivity. This requires careful calibration and often the combination of multiple exposures at different depths. Image processing techniques such as stacking and background subtraction become critical for revealing the faint halo. These challenges highlight the limits of current technology, but also showcase the ingenuity of observational astronomy. Scaling relations derived from these observations provide broader context. By plotting IC 1101 on diagrams that relate luminosity, velocity, dispersion, and size, astronomers test whether empirical laws established for smaller galaxies extend to the most massive cases. Deviations can indicate that additional processes such as environmental effects or extreme feedback play larger roles at the high mass end. In the case of IC 1101, its size and brightness push it to the extreme edges of these relations, making it a natural laboratory for exploring the limits of galaxy formation theories. Comparisons with simulations offer another layer of analysis. Numerical models of galaxy and cluster evolution predict how central giants should grow, what their halos should look like, and how their black holes should influence their surroundings. Observational data from IC 1101 can be tested against these predictions, validating or refining the models. When simulations reproduce the observed luminosity profiles and mass distributions, confidence grows in the underlying cosmological framework. When discrepancies appear, they point to missing physics or assumptions that need adjustment. IC 1101 therefore serves as a benchmark for theoretical work. Future instruments promise even sharper views. The Vera C. Rubin Observatory will conduct deep, wide-field imaging mapping halos of giant galaxies with unprecedented detail. The James Webb Space Telescope continues to extend infrared studies, probing stellar populations and mass distributions with great accuracy. Next-generation X-ray observatories such as Athena will measure turbulence and sound waves in the intracluster medium, revealing how energy from the black hole is transported. Radio arrays like the Square Kilometre Array will detect faint relics of past jet activity, filling gaps in the picture of feedback cycles. Each advance will bring IC 1101 into clearer focus despite its distance. The importance of IC 1101 lies not only in its extremity, but also in the way it demonstrates the power of multi-wavelength astronomy. No single observation could describe its star's gas and black hole together. Only by combining optical, infrared, X-ray and radio data can astronomers build a complete view of the largest galaxy in the observable universe. IC 1101 stands as a natural observatory, its size and luminosity turning it into a test case for every technique available. By studying it across the spectrum, researchers uncover not only the nature of one galaxy, but also the processes that govern the evolution of cosmic structures at the very largest scales. IC 1101, as the brightest cluster galaxy of Abell 2029, sits at the intersection of numerous scaling relations that connect the masses of galaxies, their central black holes, and the environments in which they reside. These empirical laws established from surveys of thousands of galaxies provide powerful tools for estimating otherwise unobservable quantities. The question is whether they remain valid at the extreme end of mass and size represented by IC 1101. Its position on diagrams that relate luminosity, stellar velocity dispersion, effective radius and black hole mass often falls near or beyond the edges of established trends. Studying this galaxy therefore helps determine whether the rules of galaxy formation apply universally or whether special conditions in dense clusters produce outliers. One such relation is the M-sigma relation, which ties black hole mass to the velocity dispersion of stars in the bulge. For most galaxies, this relation holds tightly, suggesting a fundamental link between bulge growth and black hole accretion. In IC 1101, velocity dispersions measured at several hundred kilometers per second predict a central black hole with a mass in the tens of billions of solar masses. This value aligns with expectations from scaling, yet it also stretches the relation into a regime where direct measurements are difficult. The consistency supports the idea that the same processes regulating bulge and black hole growth operate even in the most massive systems, though uncertainties remain when extrapolating so far. Another scaling relation involves total luminosity. The Faber-Jackson relation links a galaxy's luminosity with its stellar velocity dispersion, while the fundamental plane relates luminosity, effective radius and dispersion. IC 1101 pushes all three quantities to their extremes. Its luminosity surpasses 10 trillion suns, its effective radius reaches hundreds of kiloparsecs, and its dispersions rank among the highest measured. Plotted on the fundamental plane, it lies near the upper edge, indicating that while the relation still applies, IC 1101 represents a boundary case. This boundary helps astronomers test whether structural scaling is continuous or whether central cluster galaxies form a separate class. The relationship between galaxy mass and dark matter, halo mass, is another important connection. In ordinary galaxies, stellar mass is a small fraction of the total halo mass. For IC 1101, the ratio is even smaller, with the dark matter halo outweighing stars and gas by large factors. This places the galaxy in line with cosmological predictions which state that baryons should never dominate the mass budget of clusters. Observations of IC 1101's dynamics and lensing effects confirm that its halo mass is among the largest inferred for any galaxy, making it a prime example of how baryonic matter traces but does not fully represent the underlying dark matter structure. Comparisons with other brightest cluster galaxies reveal both similarities and differences. Like IC 1101, they exhibit extended halos, old stellar populations, and quiescent star formation histories. However, IC 1101's size and luminosity exceed most others, making it exceptional even within its class. This raises the possibility that scaling relations may bend slightly at the very highest masses, reflecting the unique merger histories and environments of the largest clusters. By carefully measuring such deviations, astronomers refine models of galaxy formation, distinguishing between universal processes and those specific to cluster cores. The mass-to-light ratio offers another diagnostic. In smaller galaxies, ratios of stellar mass to luminosity are relatively stable, but in IC 1101 the inclusion of dark matter and hot gas drives the ratio far higher. This reflects the dominance of non-stellar components in cluster environments. When compared with cosmological models, the ratios observed in Abell 2029 match those expected for the universe as a whole, reinforcing the idea that clusters are fair samples of cosmic matter distribution. IC 1101, as the most luminous member, embodies this balance, shining with trillions of suns but accounting for only a small fraction of the total mass. Scaling relations also extend to the distribution of globular clusters. Studies show that the number of globular clusters correlates with galaxy mass and halo size. IC 1101 hosts vast populations of these clusters stretching far into its halo. Their abundance confirms the extraordinary mass of the system and provides yet another line of evidence consistent with scaling laws. Each globular cluster is a relic of early star formation, and their sheer numbers in IC 1101 reflect the intensity of its early growth and the multitude of mergers that have added to its collection over time. The testing of scaling relations in IC 1101 has implications for cosmology. If the galaxy aligns with established trends, it suggests that the processes driving galaxy and black hole coevolution are universal, extending smoothly from dwarfs to giants. If it deviates, then new physics or additional mechanisms may be required to explain the most massive systems. Current data indicate broad consistency, but with hints of bending at the high mass end, perhaps due to the special conditions in cluster centers. These subtle differences are important for refining models of structure formation and for understanding how feedback environment and mergers combine at the extremes. Future observations will continue to probe these relations. Larger surveys will expand the sample of brightest cluster galaxies, allowing statistical comparisons. Improved instruments will measure velocity dispersions and stellar populations, with greater accuracy reducing uncertainties in mass estimates. advanced simulations will incorporate more detailed physics of feedback and environment, predicting exactly how relations should behave at the top end. IC 1101 will remain a touchstone in these efforts, serving as both a data point and a benchmark against which theories are tested. The study of scaling relations in IC 1101 underscores the interconnectedness of galaxy properties. Luminosity, velocity, dispersion, radius, and black hole mass are not independent but link through physical processes of formation and evolution. By pushing these relations to their limits, IC 1101 reveals both their strengths and their limitations. Its extreme size and brightness do not exempt it from the underlying rules of cosmic structure, but instead demonstrate how those rules manifest in the most massive environments. In this way, the largest galaxy known provides insight into the universal mechanisms that shape galaxies of every scale.